Okay, implicit derivatives are almost always one of the 6 free response questions, okay? So these are pretty important to learn, and it's also going to kind of use a different kind of algebra review. So what is an implicit function? And what we've been doing up until now when y is isolated, that's called explicit. So all of the derivatives so far are explicit derivative rules. There's only one type of implicit derivative, and basically that means that y is not by itself. Now, even if you can get y alone, it's not preferred that you do. So you just want to start with whatever function it is using that, okay? And most of the times you're not going to be able to isolate y, so don't even bother trying, okay? So, implicit derivatives, when differentiating with respect to x, okay? So x is going to be the variable, and they're not going to change these on you because it's tricky enough. But any term with x, when you take its derivative, is normal, okay? Any term with y, since y is a function, then you must differentiate that using the chain rule. And we really use a notation, dy dx, to denote that variable. I don't even use y prime because it's just really easy to get lost, okay? You'll be able to see dy dx, and you'll need that. So look at the first example. We're going to kind of do this in 2 parts. So the first example is just like normal. The function is x cubed. So if I take the derivative with respect to the x variable, it's just a power rule, 3x squared. And what happens is if I really have a chain rule here, I think of it as the derivative of x with respect to x. And d over x over dx, that's 1. That's why we never see this, okay? We just see it as 3x squared. So that's always been there. We just don't write it. All right, so let's look at number 2. X is the variable. Y is a function. So when I take the derivative, it is going to follow a power rule. But then I have to account that it's the derivative of the y function with respect to the x. And then we'll learn something about this later. Same thing here. V is the variable, t is the variable. So v is just going to be your function. So the derivative of v is 1 because it's like x. And then I have to account for that was the function, so it's dv over dt. Okay? Most of the time we will stick to y. So let's do some that are a little harder because then that will get us ready for the next problem. So addition is the same, we do them separately. The derivative of x is normal, it's just 1. The derivative of 3y is 3, and then I had to take the derivative of the function. All right, number 4, product rule, 1 and 2. So 1, the derivative of 2 is a power rule, so 2y, and we did a y derivative. That's the way I think of it when I want to know if I put dy dx there or not. Did you do a derivative? Then put it. If you didn't do a derivative, don't put it. Plus 2, see that doesn't get it, and then d1. Okay. All right, so now we're going to be given different problems to do with this, and so we need a couple more rules. The main rule is we're going to take the derivative, that's normal, but we want to get dy dx alone because that stands for the derivative. Okay? So whether or not you've realized it, like when we had y equals x squared, well, I always wrote this as y prime, but remember I could write that as dy dx equals 2x. So dy dx was always isolated. We just haven't made that connection until we get to implicit functions. Okay, so that's what we really need to do. So up here, we won't leave our answers like that. We'll have them set equal to things and we'll get them all by themselves. Like, look at these. It says find the equation for the slope of each line. And you're like, well, there's no point. Given. Slope was another meaning for the general derivative. Okay? If I want a specific tangent slope, I have to give you a value where. All right, so these get pretty complicated. Addition and subtraction, we're going to do them separate. So power rule, 3y squared, and we did a y derivative. Y squared is 2y, and we did another y derivative. And this one, -5, oops, and we did a y derivative. I already had the minus there, that's why I took that off. A regular power rule, and the derivative of -4, don't forget, it's just 0. So now the idea is we want to get dy dx alone. So this is one term, all one term. So we want to move all the non-dy dx terms to the other side. Because what happens is on this side, we're going to factor out dy dx. If I add 2x to the right, so then to get dy dx's are being multiplied, and we can divide. So you don't have to get y alone, you have to get dy dx alone. Okay, so let's look at our next example. So our first term is going to be a product rule. 1 d2 plus 2 d1 minus the derivative of y is 1, and we did a y. The derivative of x is 1. So this is all one term, one term, one term, and one term. So we want to move this one to the right side. So we're going to subtract, and I'm just going to put them in order. These two terms are still on the left, so we can factor out that dy dx. I forgot a 3 here. Okay. So to get dy dx alone, we'll divide. This stays on top, and this goes in the bottom. We can common factor, but you typically won't see it on implicit derivatives. Okay? Now, one of the important uses, and it actually helps you, is when we want to find a specific tangent slope, because it actually means less simplifying. So if I want to find the tangent slope, we're going to take the derivative. And then they give us an x and a y value. So 1, you're going to do your derivative. I don't isolate. We're going to substitute xy. Then we isolate. It's going to be a lot easier if we wait. Okay? But it's really a choice. So on our left side, it's going to be a chain rule, the inside and the outside. So we're going to start with the power rule. So we bring the 6 down, the inside stays the same, and we subtract 1. Then we take the derivative of the inside. So power rule, but we did a y derivative, and that's the left. On the right side, that 100 can stay there, but it's a lot easier if I keep that with the x. And then my y is going to be 2. So we've got a product rule. 1 d2 would be 1 dy dx plus 2 and the derivative of 1. Now, that's my general derivative. And I literally would just plug in x and y right now. So 6, 3 squared plus 1 squared. Because see, this is really complicated. 2 times 3, 2 times 1, 100, what's x? 3 dy dx, and then 1 times 100. And we just start cleaning this up. What's that? 9 plus 1, so that's 10. So we get 60. What's that? 6 plus 2 dy dx equals 300. So we're going to want to distribute first. And then get our dy dx terms to one side and our other terms to the other. So like, I am just going to move this to the left and move this one over there. So if we subtract 360 and subtract 300, we're left with negative 180, negative 260. So to get x alone, dy dx alone, we'll divide by negative 180. So two negatives make a positive. I could divide by 10, and I could divide by 2. So that is my tangent slope at that point. Lots of work. I love it, but I know it is a lot. All right, last example, we're going to find a second derivative. We can divide by 4. I probably will. So xy equals 10 over 4 is going to be 5/2. But that's still the original. This is 1, that's 2. So I've got 1 d2 plus 2 d1. Derivative of 5/2 is 0. We need to get dy dx alone, so I'll write this nicer. We're going to move the y to the other side, and then divide by x. That's our first derivative. So now our second derivative is, we're going to take the derivative of the left. So if that's the first derivative, then remember it's d2y over dx squared. That's the notation. And then on the right side, we need to do a quotient rule. So I'm going to make this with the top. So pick where you want your negative. So I get low, d high is negative 1 dy dx. Low d high minus high d low, all over low squared. Now, this is the tricky part. Paying attention? We can't have a derivative in a derivative. So, by substitution, this is negative y over x. And this is where the real fun comes in. This one's actually pretty nice to you. So, if I write this nicer so you can see what we have, I would have two negatives make a positive, so those go away. X reduces by x, so you might have to get a common denominator. Ours reduces, which is actually really nice. And so all we're left with is y. Two negatives make a positive over this. But that's where the real math might come in, is if you had to get that common denominator. I can simplify this to say 2y over x squared. Okay? So on your student practice, you probably have a little more complicated second derivative. Okay? All right, well, try your practice and let me know if you have any questions.